Hi, in this video, we're going to start talking about the language of models. So what is a model? We use models to explain the relationship between variables and to make predictions. For now, we're going to focus on linear models, so where the relationship between the two variables is linear. But remember that there are many other types of models too. So here I have an example of a nonlinear growth, for example. And we're going to touch on some of these nonlinear models as well during the course of this course, but many of the other models that you can fit are going to be beyond what we're covering in Introduction to Data Science. The data set that we're going to be working with for a majority of the videos for the modeling week is going to be this data set called Paris painting. So where does this data come from? The source of these data is actually printed catalogs of 28 auction sales from Paris from 1764 to 1780. So this is really historical data. The curators of the data were two PhD students in the Duke Art Law and Markets Initiative at the time of putting together this data set. Their names are Sandra van Ginhoven and Hilary Koch-Kronheim. They basically went through, I think about 3,393 auction catalogs. So these are the pamphlets that were handed out during the auctions for the sale of these paintings. And they looked at the descriptions on these catalogs and created and tabulated these data. The information they tabulated included things like their prices and descriptive details from the sales catalog, over 60 variables. So the data is stored in a CSV file called Paris Paintings, and we're going to read that in with the read_CSV function, and I'm just going to name it PP for Paris Paintings, and that's what we're going to be referring to for the remainder of the slides. And you should also note that as I'm reading in the data, I have noticed that since these were all human entered data, there were different conventions used for NAs, potentially based on who entered it, since two people did, and potentially just haphazardly. So in some of the cases, N/A were put in the cells to indicate NA. Sometimes the cell was just empty, and sometimes the capital letters NA were used. So we're basically saying any one of these might be should be considered as NAs in our data. I'm not going to play this video here right now, but if you're not familiar with painting auctions, which I have to be honest, I was not, I would recommend watching this very brief video from Sotheby's, where they do they've actually filmed things during the time of an auction where people are calling in and people are kind of placing prices based on whoever they're representing at the time at the auction, and these paintings are selling for millions of dollars or pounds. So I would recommend giving that a look. But something you will recognize when you watch the video is that the people who are at the auction are looking at these pamphlets, and on these pamphlets there's even the picture of the painting. But if you think about it, back in the 1700s, that was not a possibility. I mean, right now, I think if you go to the Sotheby's website, you can browse through their pieces that are going to be auctioned. They have an app. There's all this other way of getting information about what is about to go on the auction. Back in the day, auctions looked a little less electronic, right? Maybe it looked a little more like this. So here is a painting from Paris that's basically depicting an 18th century auction from Paris. So this is probably where our data was collected, basically. Here's the reason why these data were originally curated. So as I said, these PhD students were interested in kind of the art market and also a historical look at it. And if you look at that window of the years that we are going to be, that our data comes from, we can see an increase in the number of sales in the Paris auction market. So the art history students who were also interested in the economics of art were interested in, we wonder what was going on. What were the auctioneers doing anything to kind of motivate these sales? And let's take a look at one of the data points from our data set. So this is one of the pictures that ends up being a row in our data set that was auctioned off. So it is We can see it's a landscape painting. There's a horse in the middle. There are some kids around. There's some trees, lots and lots of people in the painting. And let's take a look now at the auction catalog. The auction catalogs are actually in French, as you can imagine. So here's an English translation on the other side as well. Note again that we don't have pictures in the auction catalog, so the auctioneers actually had to give lots of verbal description of what this is going to be like, so people coming to the auction have a sense of what they might be bidding for. So 2 paintings, so it sounds like this is one of 2 paintings that were sold as a pair, very rich in composition, of a beautiful execution, and whose merit is very remarkable. Each 17 inches, 3 lines high, 23 inches wide. So let's remember those points. Painted on wood, comes from so on and so forth. And then it describes, it shows in the front of a child on a white horse, a man who gives the horn to gather the dogs, a falconer, and other figures nicely distributed across the width of the painting, so on and so forth. So the data set basically has been tabulated based off of descriptions like this. In some of the cases, the data curators had access to the painting, like the one I just showed, but in many of the cases they did not, and so they were just basing it off of these auction catalog entries. This is what the data they put together looks like. So that highlighted row is basically that same painting. You can see in the subject column the name of the painting, and you can also see, for example, the numbers 17.25. So in the middle image there, height in inches is 17.25 and the width in inches is 23. So those were from the description as well. We can take another look at that same data set. So here I've read in the data, and so we can see that we have 61 columns worth of information. We can see the name of the painting here. Because the E had an accent on it, that doesn't necessarily get read in as easily, so we're kind of seeing the Unicode character for that as well. But we can see other information about it. What was it sold with? So its name has like an 89A, so the 89B is probably the other half of this painting that it was sold together with, height, width, and the surface area, the material. So for example, the material category was wood, which is another thing we read. And we can basically see a lot of information about the painting here. This is basically the data set that we're going to be working with. The original reason for collecting these data were to try to model the prices of these paintings, and that's something we're going to look at as well. And especially the data curators were interested in seeing, do the auctioneers do something to promote the price of the paintings? For example, do they pair certain paintings up together? How do they describe these paintings, and what features do they highlight? What features that are highlighted are associated with higher prices, for example? So we're going to touch on some of these, but we're going to start simple with our modeling. So let's start modeling the relationship between variables, and we're going to take a look at the height of these paintings. So these heights are in inches, remember. We see a right skewed distribution, and so some of the really large paintings are very, very large, 120 inches. And the widths of these paintings, we are also seeing go even wide, even bigger, also right skewed, but we have some paintings that are above 200 inches in width. So that's quite large, and it seems like those are probably like the landscape paintings that are much bigger on the width. We can represent relationships between these two variables using functions, right? So we can think of models as functions. A function is ultimately a mathematical concept, the relationship between an output and one or more inputs. So for example, if you have a function, you can plug in the inputs and receive back the output. If you have the formula y equals 3x plus y, for example, that's a function with input x and output y. If x is 5, then y is 22. All I'm doing is plugging in 5 for x, multiplying it by 3, adding 7 to it. Hopefully this is a straightforward concept, but models are basically built off of this concept. Here is the relationship between the heights and weights of these paintings. And we're also seeing that blue line in the middle, and that basically represents the model that we're fitting to quantify the relationship between these two variables. Some striking things about that model is that it has a positive slope, so which means that as the width of our paintings increase, so do their heights, which hopefully makes sense, right? If the painting is getting bigger, it's getting bigger. For these slides, I have also given you the code for them as well, but we're going to focus on the code more in the following videos as well. So you are obviously welcome to take a peek at the code to see how we fit these things, especially here. Let's focus on for a second and remind ourselves how we fit that best fit line. We're fitting a smooth line over these data using a method of linear model. So we're basically drawing a line between them. Right? We also see some warnings. We have 258 rows containing non-finite or missing values. So these are probably the paintings for which we don't have height or width information, and hence we can't actually represent them in the data, and neither can we use them as we're fitting this model that we're representing on the model. Another thing I want to draw your attention to on the plot, and it is a little bit faint, so you may need to get closer to the slides here, but there is also this gray band around the blue line. So the blue line is the model, but we also have some measure of uncertainty around it. Obviously, we have data. That's a sample data. We don't have data on all of the paintings, right? So there's some uncertainty around our model estimates. And this is something we're going to talk in a much more principled way about a little bit later in the course. How do we quantify that uncertainty? Why is that gray band only a little bit wide as opposed to much wider? So we're going to talk about all of that in a little bit in the course. But for now, it's important to, one, know that when you use the geom smooth function in ggplot2, by default, it does give you that measure of uncertainty. That is something you can turn off that I'll show in a second, but it is there by default because it is an important consideration. And number two, that uncertainty, the width of that gray band is basically a measure of the uncertainty. So the wider it is, the more uncertain, the more uncertainty we have around the model estimates. We can, as I said, draw the plot without the measure of uncertainty. So for that, in the geom smooth function, we would set the SE for your standard error parameter to false. We can make different cosmetic choices. So here I have this really chunky purple line that's dashed. So that I've changed the color of the line. I've used some hex code for it that represents purple. The line type is dashed. You have some other options like dotted and whatnot, and you can take a look at all of these options in the ggplot2 reference. And also I've increased the size of the line, which basically ends up affecting its thickness. We can also use other smoothing measures. So here we have a generalized additive model, which we're not going to talk a whole lot about in this class, and also a low S fit. So this is basically gives us not a linear model, but a curved fit between these two. And we're going to touch on this a bit more in terms of how that estimate is being done. But the way we change the smoothing method is basically in the method parameter of the geom smooth function. So a little bit of vocabulary. Our response variable is the variable whose behavior or variation you're trying to understand, and it goes on the y-axis. The explanatory variable or variables are the other variables that you want to use to explain the variation in the response, and they go on the x-axis. Obviously, if you only have one x, then it makes sense that that goes on the x-axis. If we have many explanatory variables, then we're no longer talking about a two-dimensional plot, and it becomes a little bit harder to visualize. The predicted value is the output of the model function. So the model function gives the typical or the expected value of the response variable, conditioning on the explanatory variable. So given a value of x, what would we expect y to be under this model? The residuals are a measure of how far each case is from its predicted value based on a particular model. So we need to know the predicted value in order to be able to calculate our residuals. The way we calculate the residual is it's always observed value minus the predicted value. And they tell us how far above or below the expected value each case is. You can imagine if your residuals are 0, basically that means your observed values match exactly your predicted value. So you were able to predict with no uncertainty every single observation. Probably not going to happen, and it's not expected to happen. But the smaller your residuals are, the better a job your model is doing in predicting the actual results. So if we actually take a look back at this visualization, the scatter plot, that purple line in the middle is again our linear model fit. On top, so where the observed data, the points in our data are above the predicted values on the line, we have positive residuals. And in the bottom, where the observed values of the points are below the predicted, we have negative residuals. And here's the code for creating that visualization. I would say I wouldn't worry too much about it because I'm doing a bunch of stuff that we haven't really covered yet, but we will by the end of the week. But in case you were interested in seeing how I actually did that coloring, I created a new variable that's like the residual, but a categorical variable where I said if it's, if the values are greater than 0, do something, and if they're less than 0, do something else. So let's take a look at this plot. The plot below displays the relationship between height and width of paintings. The only difference from the previous plots that we've seen is that it uses a smaller alpha value. So the geom point uses a smaller alpha value than 1, making the point somewhat transparent. What feature is apparent in this plot that was not as apparent in the previous plots? And what might be the reason for this feature? I'm going to give you a second to think about that. So if you're thinking we're kind of seeing a V in the plot, you're on the right track. So what might be the reason for this feature? Let's talk a little bit about paintings. We have landscape paintings or portrait paintings. So landscape painting is the depiction in art of landscapes, natural scenery, such as mountains, valleys, trees, rivers, forests, especially where the main subject is a wide view, with elements arranged into a coherent composition. And these paintings tend to be wider than they're long. And a portrait painting is a genre in painting where the intent is generally to depict a human subject, oftentimes a single one, sometimes multiple. Portrait paintings tend to be longer than they're wide. So, if actually we color these data by whether or not the painting has landscape features, so this is not just about is it wider than it's longer, but we're looking to see in the description, in the catalog description, were there landscape features that were mentioned? And so 0 means no and 1 means yes. And so we color these points by that. The orange points represent no landscape features and the purple points represent the landscape features. So how, if at all, does the relationship between width and height of paintings vary by whether or not they have landscape elements? Well, we can see that the slopes of these two lines, if we actually separate our data into two based on their whether they have landscape features or not, and fit models to each of them individually, we can see that we're seeing a slightly different slope. They're still both positive slopes, which is what we would expect. Whether your painting is a portrait or landscape, you would expect that if it's getting bigger in one dimension, it's going to get bigger in the other dimension as well. But the rate at which these change actually varies. So here, we've basically added another variable into our visualization, and we've basically added a color aesthetic. The variable that captures whether there were any landscape features in the data set is called lands all, but it's coded as a 0, 1 variable, which as we read in the data from a CSV file, R will initially think of as a numeric variable, but really we want R to consider that as a categorical variable. 0 means no and 1 means yes, so we wrap that in the factor function. And once we do that, and then we add a geom smooth layer to our visualization, by default, ggplot2 will fit the two different models for the two different categories and actually give us the lines for those. So we are seeing that how height and width are related seems to be potentially that in how height and width are related, whether or not the painting has landscape features might be a factor. This hopefully makes sense conceptually, and we can see in the data that it might make sense empirically as well. So another thing we might want to talk about is extending these regression lines. So when we take a look at the previous plot, so I'm going to go back to this, we could see that the orange line extends almost throughout the entire visualization, but the purple line does not. And why is that happening? Well, why that's happening is that for the paintings that are like represented in purple, their widths only go as far as 200 or 100 inches, right? But they're not going much farther than that. And therefore, when we fit the model, we don't want to just extend that line all the way out. That would be what we call extrapolation. If we were to extend that line all the way out, we would be saying that whatever relationship holds between height and width for the paintings for which we have observed data, we would be assuming that that relationship extends out into the future as well. And that's what we call extrapolation. And we want to be very, very careful when we're doing extrapolation. Oftentimes you might hear, don't ever do extrapolation, and there's value to that statement. But if you think about it, what about people who do forecasting? Weather forecasting, financial forecasting, they're always extrapolating. They're looking at data in the past and they're trying to predict the future. They never have data from the future. So in a way, extrapolation is built into some of the models that some of us work with, but those tend to be slightly different models. Maybe they're looking at what we call time series models, or maybe they're fully acknowledging the fact that there's going to be lots of uncertainty in their predictions and being using methods that allow them to be careful about this uncertainty. But in general, when we're looking at retrospective data like this, we do want to be very careful about extrapolation, and generally you will hear don't extrapolate because we really have no evidence that that relationship between height and width for the paintings that have landscape features and that are between 0 and 100 inches wide may not necessarily hold for paintings that are much bigger than that in width. If you want to get those lines to extend out completely in the geom smooth function, there's an argument called full range that is false by default, but you can turn that to true. So models can sometimes reveal patterns that are not evident in the graph of the data. This is a great advantage of modeling over simple visual inspection of data, but there's a real risk that a model is imposing structure that's not really there on the scatter of the data, just as people, imagine animal shapes in the stars. So a skeptical approach is always warranted. Just because you fit a model does not necessarily mean that that was the right thing to do, that that's the right relationship between the two variables. So we're going to learn a little bit about diagnostics for models that might allow us to check, have the models I fit actually is the data that I've fit these models to actually satisfy the conditions that are required for fitting these models? But even when the answer is yes to those, that does not necessarily mean that you've done the right thing, that you have uncovered some relationship that was truly there, and now the model has revealed for you. And sometimes it might. And so that's why we say a skeptical approach is always warranted. We also think about the variation around the model. So that's that scatter, that gray band that we were seeing. And it's just as important as the model, if not more. Statistics is the explanation of variation in the context of what remains unexplained. So lots of what we do as statisticians are actually about quantifying that uncertainty. So the scatter around the line suggests that there might be other factors that account for large parts of painting to painting variability, or perhaps just randomness plays a big role, and we don't really know which one is which. Adding more explanatory variables to a model can sometimes usefully reduce the size of the scatter around the model. And we're going to talk more about this later when we look at models with multiple predictors. So if the scatter is driven by, it can be accounted for other factors, then as we add more variables to our model, that scatter of the residuals is going to shrink. But if it's not, and it's just randomness, then perhaps it's not going to shrink as you add more variables to your model. So how do we use models? There are two major main uses of models. One is explanation, where we characterize the relationship between y and x via slopes for numerical explanatory variables or differences for categorical explanatory variables. And prediction is another use where we plug in x and get the predicted y. So let's think about this. Say you're watching Netflix, okay? And you finish your whatever show you were watching or movie you were watching. And what does Netflix do? It says, you might be interested in this next one. Or you're shopping on Amazon and you buy something and it says, you might be interested in this thing as well. There, the model is doing a prediction for you. It's looking at data from you that you've provided based on what you've watched so far, any other information you may have willingly or unwillingly shared with these websites to make a prediction to see, based on what we know about you, we believe the model predicts that you might like this next, and that's what it offers to you. There, the goal is prediction, and what these businesses really want is to get their prediction correct. On the other hand, let's think about this. Perhaps we have a researcher who's studying what are the watching patterns for a certain age group or a certain socioeconomic group within a community. There, they may not be as interested in the prediction aspect of things, but actually quantifying the relationship between certain demographics about people and what they like to watch, or why they choose to watch something and not choose to watch something else. So they might be more interested in explanatory models. When it comes to fitting these models, the process is the same regardless of which one you're doing. But when it comes to picking which model is the most useful for your use case, the process and the decision criteria may be different depending on if you're trying to do prediction or if you're trying to do explanation. In the next video, we're going to talk more about interpreting models, where hopefully these ideas of explanation and prediction will settle in a little bit more.